did I give you the value for H?
Yes.
Would that possibly be the very last thing that we did?
Yes.
Yep.
So 6.626 times 10 to the negative 34th joules seconds.
Yep.
Awesome. All right. Because now we're going to start getting into the relationships between those two equations. For number 6, a line spectrum is produced when an electron moves from one energy level to a lower energy level. So that would be what? B?
Yes.
Line spectrum is produced when an electron moves from one energy level to a lower energy level. Anyone get that one right? Good. Anyone 6 for 6? So that would be the end of that. Okay. Now, I forgot to get this out, and really, I don't know where I'm going to find this. I had to cover Connie's class last period. I was going to get this stuff out, but things get changed. Can't remember covering what was the number. Oh. Things here. It's here.
Yeah, that's
Some of you guys seen one of these yet? Okay, we have one. You seen one of these? Okay. Then you'll be my mom. Oh, that's right. You already brought me some to the other one. All right. Volunteers / all right. I cannot guarantee how well all of you did. Has anyone ever used these before? Yay, nay, no one. Okay. How many? Gosh, I got a bunch of people in here. Let's see what happens. We may end up having to share. These are the answers to one of the questions. They really are. Well, I'm going to let you guys make that decision. Someone asked me if we should pass them out. You can't use all of them at once, so.
Yes. Oh, you're making one more.
I will. So, funny little story. Can you catch it? Seriously, catch it. Okay, can you catch it? Thank you. Nice catch. Nicely done. All right. Does everyone have one? Did everyone get one? Okay, cool. And again, I can't guarantee whether they all work or not, but funny little story before we start playing with this. I videotaped the thing yesterday, and I videotaped, or whatever you not video, but I recorded my lecture for my regular chemistry classes also. And of course now it's and I made the comment like I've usually made, or oh my gosh, I have to do this like X number of times a day. And I said, but now that my classes have split, you guys are doing something different than the regular kids, it makes my life a little bit less boring. So I made that comment to my 4th period class. And they said, well, what you should do is video the lecture and then just show it the rest of the day.
Do you actually do that?
Okay, so 8th period. Kids all walked in, I said, get out your notes, blah, 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 blah. Set up the thing, turned on the smart, whatever board thing, hit play, walked out. They were all like, so I went over a little in the corner somewhere and hid, so I could kind of see some kids. They were all like looking at each other. They were just stunned. Hilarious. And so I kind of came back and I said, so how'd that go? They're like, that's bad. I said, well, it's the same thing I did in my other class. I said, but we can't interact. I said, you don't anyway. No, actually, but what I did say was, I said, you know what, this is going to make it more boring for me. So I got to come back and I said, how else can I make fun for? The more classes I teach, the more kids I can make fun of. So yes, Emma, that was for you. But that's if I just press play, then I can't make fun of people, right, Serena? Okay. All right, moving on. Okay, these things are called spectroscopes. This is the end that you look through. This is the end that you look through. What I'm going to have you do right now is point it up to one of the fluorescent lights, doesn't really matter which one, and describe to me what you see.
The color.
What?
Do you see the entire visible spectrum?
Yes.
From red through purple?
No.
Try that. You should see the entire spectrum.
I see
Can you
yellow.
it? Can you see it? It's yellow.
I don't see yellow.
Ah, there you go. Okay, so you see the entire spectrum, right?
Why is yours like that?
Awesome. Now, what we're going, this room sucks. It really sucks. I apologize for that, but there's nothing I can do. Is it that one? Is that the light that sucks? Yeah, that's the light that sucks right there. When I've taught in Homan's room, which I've done at various points in time, his ceiling is flat. I always get up and unscrew the light bulbs, okay, just to make it as dark as possible, okay? This room will suck a little bit. So we'll do the best we can. Look. Anybody ever have a class in 2019? I think it would have been Ruffin might have been in there. Okay, that room is awesome for this demonstration because there's no light. And they used to, those little windows that used to be at the top of the classroom along the wall. They go out to the hallway, right? I saw you go out and turn off the hallway lights. That room was so dark you couldn't even see your hand in front of your face. It was awesome. That's what I'm saying. That light is really dark. All right, so I'm going to have you end up looking back here because it's less light. I got back here. Oh, I'm sorry. No, not yet. Maybe. Okay. What I'm going to do is show you what this the line spectrum that was mentioned in question number 6. Okay? What's happening is you guys remember the energy levels, right?
Yes.
The electrons have a tendency to be at that lowest energy level possible. Why? What is causing the electrons to be at the lowest energy level possible? Why do the electrons hang around the atom in the first place? What are they doing constantly? Moving around, zooming around all over the place. Why don't they just leave? Think this through. What's that? To what? They're attracted to the protons in the nucleus. Okay? So there's a kind of a balance going on. They're zooming around all over the place. They could easily leave. However, being negatively charged, they're attracted to the positively charged nucleus. Everything so far so good, right? We're going to get into how attracted they are for the nucleus a little bit later here. But anyway, they're attracted to the nucleus. Now, in order for them to jump up to another energy level, okay, you're going to have to supply some energy to get them away from the nucleus a little bit. Does that make any sense? Okay? But that means the energy is going to be absorbed. Does anyone remember what that means, whether in terms of energy terms, in the sense of exothermic or endothermic? To get the electrons to jump up to a higher energy level, is that an endothermic or exothermic process? Endothermic, very good. Energy is added to get the electron to move up. Okay, so some energy is going to have to be supplied. That's what this thing is going to do. So when we plug it in, so we're going to use electrical energy to apply to some gas of different elements. We're going to cause the electrons to jump up to a higher energy level. But what's going to happen is them being so attracted to the nucleus, they're also going to then come back down. So they're kind of going back and forth. But every time they go back down, they're going to release some energy, which is an exothermic process. That energy is going to be released in some sort of electromagnetic radiation. As it turns out for these, it's going to be in the visible spectrum. Okay? And we're going to use these things to help us identify, well, you're going to see different colors, I guess. And then we'll go from there. All right. Let's pick. Oh, as it turns out, the entire energy level idea was studied and based on one particular element in particular. The whole energy level thing is based on hydrogen gas. And so, we'll put some hydrogen. And then I'm going to turn this on. What you're going to try and do, you see that little slit that's at the other end? Okay, when you're looking through the spectroscope, you're going to try and line that little slit up so that it's just off of this line right here. You'll see what I'm talking about here in a second. You'll play with it, you'll figure it out. So anyway, there's hydrogen gas. What you're going to attempt to do can you see that, Aaron? Did I tilt that enough that you can see it? Does that help you? I don't know about you guys. Do you guys still see it?
Yeah.
Okay. And then you should see some very distinct lines over on the spectrum side. Currently, I'm seeing very vividly red, a kind of an aqua blue, and a purple. I don't know if anyone, you should all be seeing the same thing. Are you guys seeing a very similar? A definite red, kind of a blue-green kind of color, and then a purple. Okay. What that means is, if you see that, if you see those colors through your spectroscope, that tells you, that identifies this element as hydrogen. So each element produces its own separate spectrum, line spectrum. That's what these line spectrum mean. Okay? So that's what hydrogen looks like. There's a whole thing I'm going to go into about this right now. You guys knew about the Big Bang. You guys studied the Big Bang at some sort of time in your your science classes. Some of you have, some of you haven't. Who has not? What's the Big Bang referring to? Okay, so you're aware of whether how much you got into that or not. There are really two main pieces of evidence for the Big Bang. Does anyone know what those two pieces of evidence are?
Red shift and blue shift? Or what
What's
is it?
blue shift?
Or whatever it's called.
Red shift, yes. Somebody else said something else was correct. The background radiation, the background cosmic radiation. Okay? So the two pieces of evidence are this background, and anywhere you point a radio telescope, they're going to detect some radiation. Okay, over the entire universe. Again, that's the remnants of the original Big Bang. The other thing is redshift, which is based on what concept you guys learned relative to waves. Doppler effect. Did you guys cover the Doppler effect?
Yes.
Okay. The Doppler effect is the apparent change in frequency of a wave based on the movement of either the source of the wave or the receiver of the wave. Okay. Best example of that probably if you guys have ever been stopped at a train intersection. Okay, and you hear the train coming, you see the train coming down the tracks and it blows its whistle. You ever heard the change in frequency as the train whistle goes by? So as it's approaching you, the frequency appears to be. Now, loud, you got to distinguish between frequency and loudness. There's a difference. The frequency does what as it approaches you? Appears to be higher as it comes closer to you. Then as it passes you, the frequency has a tendency to sound lower. Okay, you guys with me on that? Okay, now if you were on the train, did the frequency of the whistle change? No, it's the apparent change based on your position relative to that source that's moving. Okay? Well, the same thing happens with these things. Now we know do we know that the red end of the spectrum is the lower frequency and the purple end is the higher frequency. So infrared, so the light that we can't see, okay, that's at the lower end frequency-wise, and ultraviolet is at the higher end frequency-wise. You guys are familiar with that, right? Same thing goes with visible light, red, lower, purple, higher frequency, okay? What this redshift refers to is that what are stars made out of? Primarily.
Gas.
What's gas in particular? Hydrogen, okay? And where does the sun's energy come from? What process goes on? Does anyone know?
Nuclear fusion.
Fusion. So hydrogen is becoming first, maybe nobody knows, helium. So hydrogen is being converted into helium. Now ultimately, as that process keeps going, the helium ends up producing more and more elements, but anyway. Initially, the sun's energy comes from hydrogen undergoing nuclear fusion, which means putting atoms together to form helium. That's where all the energy comes from. Anyway, stars are made mostly of hydrogen. So all you have to do is look at any star with a spectroscope, and you should see what you just saw. The red line in the position that it was in, that blue-green line in the position that it's in, and the purple line in the position that it's in. That's what you should see. But as people start looking at the stars, they start noticing that all of those three lines are shifted just a little bit towards the red end. Okay? Towards the lower frequency. So what does that tell you that every single star is doing? Moving away. Because we remember how we just talked about that the frequency goes lower as it moves away, gets higher as it's moving towards the observer. Every single star, from our perspective, which means from all the other stars' perspective also, seems to be shifted a little bit towards the red end. That's where the redshift phrase comes in, which means that every single star is moving away from every other single star. That's the first piece of evidence they have to Big Bang. Anyway, moving on. So there's hydrogen. Now with my AP kids years ago when I used to do this, I would actually have this sheet of paper they would have to draw the spectrum for everything. So on their little sheet of paper they'd have this little rectangular box and you'd have to put a red over here, a blue-green here, and a purple here. Okay? And then ultimately I would give them an unknown and had to identify what it was. Next. Let's play with some more gases here. You guys are just going to have to rely on your memory as to whether these are different or not. Well, that's odd. Let's look out at Krypton. What time is it?
8:30. No, I was actually looking at the time. That's why I wrote it.
2 if it's different than hydrogens. There we go. I see 2 that primarily stick out. There might be a third over there, I can't really make it out. What are you guys seeing? You got a yellowish orange and a green? I saw, yeah, that's the one that was way off to the edge, and I couldn't tell if I could make it out or not. Yeah, there's a little bit of a purple over there. Not really, just, but anyway, you notice that that's different than hydrogen. There you go. That's the point. Like I was saying, each element provides its own unique spectrum. Why does each element have its own unique spectrum? Because each element has its own unique arrangement of number of electrons and arrangement of those electrons. That's why they're all different. Let's see. Remember, I used to have my students argon is argon. I used to have my students draw these things. So there's argon. Ooh. You guys getting a lot of different lines? Although really, I'm seeing a really distinct red, a really distinct blue-green. But then I see some fainter lines in between. Are you guys seeing that too? Some of that's due to this. I mean, there's nothing I can do about that. Some of that background stuff is, if this room were completely dark, you would really only see a few distinct lines. This is kind of muddling things up a little bit. All right, so anyway, that was what? Argon? And I don't want to do too many more, but I do want to show you the one that you guys are all familiar with. What gas tube are you guys familiar with? Neon, right? What color is neon? This is always hilarious. Everybody calls all these colors that you guys, oh, it's neon green, it's neon yellow, it's neon orange. Neon only has one color, and it's none of the ones that you guys are calling neon. Now, fluorescent green, fluorescent yellow, now that would be something you should call it, okay? This is what neon actually looks like. And remember, I used to have my students draw all the little lines. That line as you look at this one. This is what neon actually looks like.
Oh, come on, mister.
How about that? There's what, maybe 30 lines there? But anyway, so if anybody ever tells you that, oh, that's neon green, you now have evidence that neon is not green, it's definitely red, okay? And so it might be fluorescent or something or other. All right, so the main thing I wanted to do here was for you to see that each element produces its own spectrum. I think you can easily see that. You can leave the spectroscopes out on your next year. Please don't knock off the table. Just for fun. I purchased that device back there, the Spectrum 2